Good afternoon and welcome to our second project show for today. We have a team LDMS for Life from the University of Bern, and they will tell you where and how do we search for the signs of life on the extraterrestrial bodies. Thank you very much for joining us today. If you would like to know more about the project, please use our YouTube chat to submit your comments and questions to the team, and we will have some time after their presentation for a discussion. Now I'm happy to give the word to the team.
Hello, good afternoon, everybody. My name is Koen. I am the project manager of project number 14, LDMS for Life, like Maria said. And also, as Maria said, the thing that we've been focusing on for the last 6 months is how to find and where to find life outside of Earth. And today I want to be talking to you a little bit about that subject and show you what we've been doing over the past months. But before we dive into that, maybe to answer a question that many of you might have had in their head when you hear searching for life outside Earth is why? Why would we spend so much time and money and energy to search for life outside of Earth? And well, there are a couple of answers. I mean, of course, we are biased because we think it's an absolutely fascinating topic. But maybe it's good to realize for everyone that exploration in any kind has always been part of human nature. We've explored every nook and cranny of this Earth, and yeah, it's time to start looking outside Earth to find boundaries of living species not on this planet. And aside from this interest in it, you could also realize that the technologies that will be developed to help our search for life are things that could very, very much help us here on Earth. So it's not just a philanthropic endeavor. So to search for life, we need to have a bit of a strategy, because it's not as easy as just flying somewhere and shouting about, hello, is anyone there, and hoping for an answer. So what we need are what they call biosignatures, which are markers, chemical or biological markers, physical markers that indicate the presence of life. This can be both life that exists right now, so that's living right now, but it can also be life that has been extinct for years, decades, even millennia, up to billions of years. And so the astrobiological community, as this is called, they decided on a couple of biosignatures. And they range from very big scale, so rocks and lamination in rocks, which you could see by eye, to very, very small things like chemical signatures. And these are the ones that we will be focusing on, such as organic molecules, but also isotope ratios, so the ratio between different isotopes of the same element. So what do we actually need to search for this? Well, we need two main ingredients, let's say. We need the team, which in this case is us, and we need the tool, which is the instrument that you will see, that you now see on the right. So we are a team of 5 students, postdoc and PhD students, working from the University of Bern in Switzerland. And over the years, the group in which we work has developed a very interesting and exciting new tool to look for biosignatures. And this is actually what our project focused on, and what we will be sharing with you today.
So our department is, since decades already, since the first experiment on the moon on the Apollo 11 mission, highly involved in space exploration, in space research, and the development of new measurement techniques and instrumentation. We are involved in many current space instruments, but also very recent one, like the Rosetta mass spectrometer, the RTOF we had on the Rosetta mission. But we are also involved in many on the ongoing projects, like the Pepe Colombo mission to Mercury, with here the Bella instrument or the Strophio instrument. And maybe you heard very recently that we are also involved or providing, we have the lead with the Cheops mission, where we designed everything independently here in-house, a 30-centimeter telescope designed to search for exoplanets and also to investigate known bodies in more details. So before I go in more details, we will show you now a movie which we pre-recorded with the director of our Space Institute, but also the PI, the director of the Physics Institute. They are well-known leads in planetary missions. And now I pass by to show the movie.
I was 8 years old when Neil Armstrong first walked on the moon, and so I was always interested in space from a very early age.
Well, I was always fascinated by designs for extreme conditions, for extreme applications, so I first went into motorsports, and afterwards I ended up in space, and that's it.
First, I didn't know that you can become a space engineer in Switzerland. I thought that there was no industry, no institute that would do space stuff. When I discovered that you can, I started to orient my studies towards it, and then I was lucky to find a job here at the University of Bern, and I've never looked back since.
When I came here, I was hired for the SOHO project, the Solar and Heliospheric Observatory. I came late to this project, hardware was almost built, so I was hired more or less as a project manager to finish the hardware, organize tests, conduct the tests outside at ESA premises, at NASA premises, all the way to the launch campaign.
My first involvement with a space-related project was, I would say, the vibration test of P14 hardware here on the shaker. And P14 took off by the end of 2018 and is now flying towards me.
There's a drive there purely from a managerial point of view to keep acquiring new projects. But of course, there's also fundamentally, I'm interested as a scientist in looking at new missions and looking at performing new science.
Space projects are always interesting because they are never one like the other. Every time you have new boundary conditions, new objectives, so this is a great motivation for an engineer.
What the opportunity you have in space missions is to address big questions about our solar system, maybe beyond the solar system, outside. So questions like, why is the Earth looking like this? How does the Earth work? How does Mars, Venus work? Why are we different from Earth?
I think the first point, when you can work on something that will fly to space and help push the boundaries of what we know about space, about objects in space in the solar system, that's very passionating and very uplifting. subject of work. And the second thing, on the shaker here, sometimes we do destructive vibration tests, and then in the end you get paid to destroy stuff, and that I find really cool as well.
Resources of all kinds are a challenge. So you have limited time to realize this project. You have limited money, you have to build your instrument for the scientific questions you want to address. With limited mass you can put on a spacecraft, with limited power resources you will get from the spacecraft to operate your instrument.
I think a very challenging aspect is the environment that space is something that we don't have here on Earth. So to test the hardware that we create, we have to recreate those conditions, and the infrastructure and everything that you need to do to recreate those conditions is very complicated and expensive.
Well, it's all about people. If you have the right people at the right place, in the right moment, then the project will be, let's say, not simple, but by far not as difficult as the contrary. Technical problems are much, much easier to solve than wrong people at the wrong place. Space project can be stressful, of course, because the schedule is always tight. You can encounter problems, that's normal.
I would say quite stressful. You have to be able to handle stress, you have to be able to handle time pressure, budget pressure, you have to handle failures which come regularly because you're pushing to the limit.
It comes in phases, so early in the project it's not very stressful, but the closer you get to the delivery date, when you need to send the stuff you've done, the more stressful it gets.
It can be stressful in several areas, and there are times when it's fun and easy.
If the project is started in the right way, you have a good architecture, a good team, then it's not so stressful. A sample return mission is still on my wish list. This would be a nice thing to do before my retirement.
For me, and not just for me, finding life somewhere else in the solar system is of course a major goal, the big goal we are working towards.
Out of the list of questions that I was provided with, that is probably the hardest to answer. So I think probably the take-home message I would give you is that persistence and perseverance are very important aspects of the whole process, and if you can bring that to the table, it's good.
The questions we want to address are much broader than can be covered with a single discipline. One has to be open to learn from the others. One has to be open to establish this communication with different fields of your expertise.
I would say it's first of all, it's very gratifying to work on something that flies to space at some point, and secondly also that working to help humanity understand more about the universe is also something that I find personally very enriching.
The most important thing in space projects is really enthusiasm. There's no routine, there are standard processes, but everything is new every time. So you need enthusiasm, you need interest in new things, in new developments. That's the key. And then space will be the right thing for you.
Okay, hello back again. I hope that you enjoyed our movie, the pre-recorded movie. It was actually very fun to record that with the different person. And we can now actually go on and bring a bit closer to what we are doing with this Origin instrument. It's a new system we designed in the course of the last 2 years, I would say, to have a new instrumental setup, what you see on the left side. What we have to mention at that point, it looks very big. One side is about 1.5 meter in width. So this is actually just used to test and to simulate the space environment where we have our system to be operated. So actually the system, what we are using is the one you see here on the right side. It's also that one I show you here, maybe in the hand. So it has the size of a pet bottle. So it is a super compact system, and it's simple in slide weight and can be used straightforward, which I would like to explain you in the next couple of slides. As I said, it's a very small miniature system, and for comparison, we just added here, it's not a branding advertisement from GOP, but it has about the size of a half-liter PET bottle here shown at the right side. So the length is about 160 millimeter in length, 60 millimeter in diameter. The whole system, a flight version, would be about 2 kilograms only, and that includes like a laser system. I will explain on the next slide. We have about 15 watt power consumption, which is low. And one of the main capabilities of our system, it has the measurement capability to detect single ions or larger molecules. So we are very, very sensitive, and we are sensitive for detection of life. So on the next slide here, on the right side, what you see is actually a schematics, how this system is working. It looks very complicated. I don't want to go into this detail, but actually from scientific point of view, it's very straightforward. What we are using is a laser system, a pulse laser system, which produces 20 pulses per second. The laser pulses are forwarded with mirrors that are reflecting the pulses towards our vacuum chamber, where we have the space environment. The laser pulses hits the sample surface, where we take off shot by shot a little bit of material, and then this ablated material we can analyze afterwards in our miniature system. And from that point of view, we have the full chemical information for every laser shot we apply to the surface of interest. So that allows us actually to find maybe life.
So now Andreas has told us a bit about what we want to use and how we want to search for life. And so the next step is to ask yourself, where do we want to search for life? And actually already within our solar system, we have two very promising objects. The first of one, which you see here, which is Mars. Mars has a couple of very interesting characteristics. It's within the habitable zone, which is the radius around the sun, where it's the right temperature for water to exist. It has an atmosphere, which is very unlike many of the planets in our solar system, which is, of course, we believe, very crucial to host life. We know that there's water on Mars, very similar to Earth. The north and the south pole of Mars are covered in large sheets of ice, water ice, which you can see on the right side of the screen. And it's relatively warm compared to other solar bodies. There's, of course, one big minus, one big con, and that is that it has a very, very strongly irradiated surface, which is detrimental to any life that might exist or have existed there. And so the current idea is that if life is or was present on Mars, is that it's probably present underneath the surface, where it's shielded from this irradiation, and either signs from extinct life that have been hidden there and preserved there for a very long time might still be present, or we might even find life ones. The second target was to be at least a bit more of a surprise, which is Europa, which is a moon of Saturnus. And recent flyby missions have confirmed that the shell of this moon is a very thick layer of ice, several kilometers thick water ice. And the idea is that beneath this ice is liquid water. And this liquid water is even thought to be in contact with the very hot molten core, which would provide a lot of energy to the water and also different molecules. So very much like the hydrothermal vents, which you find on Earth on the bottom of the sea. These might be habitats for different types of life things to live. And then through cracks in the surface of the ice, this water might be eject it towards the surface where it then freezes and where it would be very, very easy to detect. Now, the third thing that we need to take into account is how we actually want to search for life. What is the strategy? And currently there are two main, let's say, streams. The most straightforward one, the one that you can most imagine, is a sample return mission, where we send a certain rover or robot to a planetary surface, where it will collect sample material and prepare it for transport back to Earth. And then eventually this material needs to be sent back to Earth, where it can be analyzed to see if it contains anything. Such a strategy is actually being developed right now for the next mission to Mars by NASA. Now, of course, as you can imagine, this is very, very complex. It needs a lot of different techniques, and everything needs to work perfectly. And in the end, you only have the material back on Earth which you happen to select. So it's limited, and it's very, very expensive. And so the second stream, and the one that we prefer, is what we call in situ analysis. And basically, this means that you do your research on the planet itself, and in this case, you only have to send back your results, which we believe is a bit more viable. So that brings us to our objectives for this IGLUNA project. We had a twofold project. On the one hand side, we wanted to show and improve the scientific capabilities of the Origin system. And the way we do this is to show in the lab that it's capable of performing measurements on chemical biosignatures. The second part of our project was to bring the science behind their system, which we can understand is maybe a bit abstract for a lot of people, to bring this closer to the people. So the way we wanted to do this is to create an interactive model of a possible future space mission, which would host our instruments, so that we could show to the public, to anyone who was interested, what we believe our instrument could contribute.
So, and that brings us actually to the next slide, how we are looking with Origin for signatures of life. I mean, I showed you on slides before how the instrument actually is working. But for what we are looking for specifically with that instrument, so let's assume we had kind of life out there, maybe microbes. This is also a discussion at the moment. When we would have microbes, we would have for sure fragments. If the microbes are not even there anymore, so they are degraded because of environment, radiation, etc. For sure, we have leftovers of proteins which are made of peptides. And when we have that, we come actually to the signature we are looking for with our system, and that's amino acids. So we know from Earth, from the life we have here on Earth, that amino acids are very, very important, let's say, building blocks of life as we know it from here on Earth. So we are looking for sure for something outside Earth which we understand, and that's the amino acids, for instance. And so we would go with with our system there, here shown with this image at the bottom, maybe on the rover. At the top of the rover, you see our small instrument at the very front at the arm. And then we start our analysis, where we shoot continuously laser pulses to the solid we may think that hosts life or hosted life. So what we are doing actually, we record, as I said before, the chemical fingerprints, and we do that on the biomolecule basis. And what we show here, that looks a bit chaotic to a non-scientific eye, but what I can tell you here as a take-home message is, for the very interesting amino acids we investigated, we find a very unique amino acid signature, which allows us to say, okay, we have this amino acid found, but furthermore, we also can tell you, or the science community, at which concentration this amino acid is present in the solid investigated. And together we have a close picture, which allows us to say indirectly, okay, there was life.
And that brings us to the second part, the second goal that we had during IGLUNA, which was to build a rover. And this rover would host Origin, and we could use it to show the public what we do. And to show you what the process was in getting this and how it came about, I want to show you a little movie. So that's what we're going to do right now, and I hope you enjoy it. welcome back, everyone. So there you see it. The rover, as you can see as well in this picture, is ready and ready for doing any type of outreach event and trying to convince people that what we have here is a very interesting and high potential technique. And with that, I think we have come to the end of our presentation. So now it's time to give the word back to Maria, and maybe you have some questions.
Thank you very much for your very interesting presentation. I see that the audience was really excited to learn more about searching for life on other planets and other places in the universe. So I have a lot of questions from our YouTube chat on that topic. But before we go to that, somebody was also asking about the project itself. So what was the most fun highlights that you had during the project?
Well, I guess we could both answer this separately, maybe. So I think for me, one of the biggest highlights was learning a lot of new things. So for instance, to develop the rover, we needed to learn how to design things in 3D sketching programs, and to learn how the 3D printing then works, to see what type of things work and what type of things don't work. So for me, the biggest highlight was for sure that after a couple of months, I realized that I gained a new skill, which I had never imagined that would happen.
Yeah, for me personally, it was clearly, I mean, I'm since working now almost more than a decade in space instrumentation, so I like the project very much. One of the highlight from my personal point of view was really, we were at the end forced, or not forced, but we had the opportunity to print and design our own rover. So I give you an example. We received a 3D printer. We never printed by ourselves. No single print, and we got the printer at the end of February. We printed until when last week about, and we had the first test last week on Saturday, and it worked smoothly. Yes, and I believe that was my personal highlight, that this was like on the point. It worked out.
Well, that's great to see that you had a lot of fun with the project itself. So now maybe let's go with the questions regarding the searching for life. Somebody is asking, can you provide a good assumption on when we will find the life outside of Earth?
Yeah, of course, this is a very difficult question to answer, because it depends on a very large number of factors. The most easily imaginable being how many missions will actually be sent in the upcoming decades. If we send one mission every 100 years, then of course it will take a long time before we find it. And if we send one every week, then it will be faster. So yeah, it's very, very difficult to make an accurate assumption. So I wouldn't try to do that, because I think the chances of me being wrong are astronomical, and the chances of me being right are miniature, let's say.
Yeah, and we have also to say that with every mission we learn something more. Right? Before, when we sent the first mission to Mars, we looked for life on the surface. Now, with the upcoming missions, we know that maybe the subsurface environment is more habitable for life as we know it. So with every mission, we increase our knowledge, and with every mission, we can more or specifically look to a certain indicator of life.
Speaking about the missions, do you think that once we detect the signs of primitive life, let's say on the Moon or on the Mars, would it be possible that those are actually the ones that were brought from Earth with the astronauts, with the equipment?
Yes, of course, this is a very, very large topic anyway in space research. The Planetary Protection Program focuses on exactly this, how we can be absolutely 100% sure that we don't contaminate any of the surfaces that we land on. So it's safe to say that basically everything that we can imagine to be done is being done to prevent this. But yeah, I know from the Moon there is an anecdote of a space mission which might have already inoculated the Moon with Earth microbes. So of course this will be it will be interesting to see. But I think even if we do get, let's say, false positives of microbes that were deposited by humans on let's say the Moon, because I think that's the only reasonable where we can expect it, we would still be able to tell that it's life that originated on Earth, because I don't think we should expect life on the Moon to be that similar to life on Earth. So maybe that we can then use to distinguish between the two.
I would like to continue on this topic, speaking of false positives. Regarding the technique itself, what are the chances of receiving the false positives using your technique, and how do you study this question?
I guess that's you.
Okay, I can go on. Yeah, false positive detection is really that's a critical point here, and many thanks that this person addressed that question to us. It has a lot to do with a lot of instruments we had on previous missions to, let's say, Mars, right? In this missions, in the recent missions, we had a lot of sample preparation as well, which may alter during the analysis the solid we are interested in to analyze. And that was one of the big discussions we had all the time, and we have really to make precautions on that. Now, taking our instrument specifically for that, it's important also to address that we are not looking only for one single amino acid, right? Because maybe that's just by chance we found something. So we are looking for a pattern we investigated, which is very important for life as we know it from Earth. So when you have already, let's say, a couple of amino acids, 5, 6, 7 amino acids, which show up at high abundances, that is actually our indicator, and that reduces these false positive detections dramatically. So this is just concerning our instrument. What happens actually on space missions is it's instrument effort. So we deploy many instruments on a planetary body to answer this question. So if only one instrument shows the flag of we found something and the other not, so the discussion starts. So we need to have like a complete set of sophisticated instruments answering that question, that we are sure we found something or not.
Thank you. I guess you convinced me and hopefully the audience as well that with this technique, the false positive should not be such a big problem in terms of the technique itself. But then I have another question. So what about the life itself? How do we know that the life on other extraterrestrial bodies would follow the same rules as life here on Earth? So what about the false positives in that sense?
Yes, I guess, but at that point, this is fully true. We don't know what life will look like. We have no idea if it will follow the criteria that we are used to from Earth. But at least in my opinion, the problem there is a bit, of course, is a valid point, and we might even get false negatives because we search for something that simply isn't there because the life that we are looking for uses completely different. For instance, they could not use amino acids, which is something that we cannot imagine, but that doesn't make it impossible. But the problem is a bit there that we don't know. So we cannot look for something that we cannot imagine. And so the best effort we can do is to look for something that we believe is viable, vital, and yeah, essential to life. So that life could really not do without it. I guess that's about the best effort we can do.
This was a very nice part of the discussion. Now I would like to address some more technical questions that we also have from our YouTube chat regarding the current project itself. So now you presented the rover with the payload, so to say, as a mock-up for interaction with the public. But now thinking about the future real missions and your instrument, what would be the best place to put the payload on the rover so that it is protected from the dust and the radiation?
Well, I guess I look over to you.
Sure. So we addressed that bit during presentation, we agree. And if I could choose a mission which I like the most, would be a Europa lander mission, because there we have like ice samples with the new observations we have, as Koen presented. We have these liquid oceans, we have these thermal vents at the core, or where at the interface between core and ocean, where life may exist. And when we would have the chance, this would be the goal, to have our instrument on the payload of such a mission.
And I think concerning maybe the place on the rover where the instrument should be to be protected, I think the current plans for missions like that is that the entire instrument suite, like Andreas told before, will always be housed inside the rover or lander, behind many protective shields and samples that will be drilled from the surface by some sort of drill collector would then be fed to the instrument suite as a whole. And so that automatically would mean that the rover, not like on our model, is outside and outstretched and vulnerable on an arm, but somewhere inside and protected. And actually, during our discussions on how to design the rover, we passed this point many times because we wanted to be as realistic as possible. But of course, it's a bit difficult to do to place the instrument inside the rover and then try to convince people, yeah, it's really in there. So just for visual purposes, we now place it outside, but realistically, it should be inside.
Now that you mentioned your ideas on the design of the rover and how realistic it is, I have a question. I think it is related to this. Somebody is asking, could a rover with this type of tire, so small, move on the uneven surface of the moon?
Please go ahead.
Yeah, well, actually, that's a funny thing, because maybe for the space enthusiasts, they might have recognized it, because it's a 1 to 2 scale model of the MERB rover, the Mars Exploration Rover B. So actually, it's a rover that has driven on the surface of another planet, in this case Mars. I'm not 100% up to date on let's say topography of the surface of Moon versus Mars, so I'm not sure if the terrain would be much rougher, but I'm assuming that it should be no problem. Of course, scaled up to twice the size.
Yeah, I mean, the Curiosity rover at the moment we have on Mars is like a car, right? Keep in mind, so this is something very big. It looked here small on our image, but this kind of instrumentation, like now on Mars, they are car size.
Thank you for your answers. I have a very technical question. What is the communication latency limits for your rover in a real-time lunar mission?
Oh, that's a good point. That's a good question, and that depends highly on where we have our instrument, right? So what we can say is typically space instrumentation on rovers, they almost operate autonomously, right? That we actually, to solve that problem, that we not need to interact all the time. So we give the instruments jobs to do, right? And as soon as we started the job, typically all the instrumentation know exactly what to do and they deliver data. Then the data is typically, depends on the orbit where we are, right? Is then sent back to Earth, and then we have pre or like post data analysis in the labs. So the instrument on the rover is typically working autonomously.
Thank you for your answer. A more general question, if you could remind us a short maybe overview of the similar existing technologies, similar ideas for searching for life.
Yes, at the moment, that's a good point. Maybe that's even a person which is involved in this project. We have a laser desorption mass spectrometer on MoMA, which will fly to the Mars as well in the near future. It's also a laser desorption mass spectrometer, but coupled to very different instruments, right? This will be one of the closest, I would say, what we are doing. I would also like to keep in mind the instrument that's like this 3D print here was already on the called LASMA in the past and was also part of the Phobos Grand mission. Unfortunately, the spacecraft died in the orbit after we left the Earth, which can happen, right? But I would say these two instruments, this LASMA instrument and this laser desorption mass spectrometer within MoMA instrument, that is, let's say, the closest what we are doing.
Yes, and then you have, of course, a lot of different techniques that will be used, which typically rely on what we believe are more complex things like wet chemistry, where things need to be extracted from the soil or derivatized with a certain chemical reagent, which adds just a lot of complexity and sample preparation before you can do your measurements. But of course, this has found a lot of use in the past.
I see I have a question in the chat. Somebody is asking, what is the price of your product? I'm not sure if they are referring to the rover itself or the instrument.
So yeah, that's a very good question, right? So So what we are designing is very unique space instruments. So this instrument here we are using in origin was developed or started to be developed in 2003, so almost 20 years back. So if we say, and if we sum up all these costs, we are easily in the millions, right? That's because mostly of personal salaries, which scales that up. Hardware point of view, if we have just to redesign something like that from mechanical point of view, this is I would say a few thousands. But what is expensive behind is the knowledge. It's the knowledge why we designed it like this, and also the knowledge or the expertise how we need to operate the system. And that is the, I would say, the most expensive part behind the heritage about the instrument.
And from rover point of view, it's actually also, let's say, in the
okay, that's a very good point. So let's say we are selected for a mission on Europa, and we have to deliver a flight version, because what we operate in the lab, this is not a flight qualified instrument. So we need to vibrate the system, we need to freeze it to -50 degrees, etc. We need a lot of radiation shielding. Also there, we scale immediately to a few millions. If we just follow all the steps, the verification tests, and then to have a flight version at the end. So we are not building like in industry thousands. But if we would do that, it's clear, and all the companies in industry have the same problem. As soon as you scale up the productivity, typically the design, the costs, they are lowered at the end.
Thanks a lot for this very detailed answer. I hope it answers the original question. I have another question. Would you like to tell us what was actually the most difficult part of the project this year? So you already told us about the most fun part, but what was the main challenge for you?
Yeah, that's a good question. Well, of course, in terms of the well, let's say for me as a project manager, it was the most challenging part was time management. We're all full-time employed somewhere else, so either as a PhD or as a postdoc student. And the IGLUNA project is not something that can be done in like 1 or 2 hours per week. It needs serious dedication. So to find for everyone the time and to bring it all together, this was very challenging.
Yeah, and for me, the coronavirus, right? Because when we started to print the rover, we have absolutely not foreseen that something like that may happen. But as soon as that started, we had serious challenges to get the materials to print it. Mm-hmm. And it starts from the simple filaments and from the motors we needed to attach to the system, the electronics. And that was also a big question mark if we really can make it or not from rover point of view of the functionality we need. Because we simply realized that we depend a lot on these supply chains, and they were affected a lot. Not only us, right? The whole society.
Well, that was great to see that even despite those challenges, you were able to complete the project. It was nice to see your rover completed. I do not see any further questions from our YouTube chat. We have a bit of time in case you would like to say a few more words.
I think we're good. I want to thank all the viewers. I hope you learned a little bit today about how to find life in space. And yeah.
And if somebody wants to have the designs to print the rover, just let us know. We are happy to deliver all the parts.
Great, thank you very much. Well, thank you, Team LDMS from Bern, for your very nice presentation. Thanks everyone for your interesting question that made this also a very nice discussion after the presentation. And we will have a talk from my guest a bit later today, so stay tuned for that. Thank you very much for watching us and have a nice day.
Thank you.
Welcome everyone to this IGLUNA virtual campaign. So as usual, we have every day an expert from the space sector presenting. So today we'd like to welcome Sylvain Chaty. He's an astrophysicist and professor at the University of Paris, and he wrote a book about the colonization of space. So today Sylvain Chaty is going to discuss the core problematic of IGLUNA. So yes, we are building technologies to sustain life on other places than Earth. But what does that mean? Where would we go? And is there a human-friendly place somewhere in the universe? So we are very looking forward to Sylvain's presentation, where he will provide us with useful background information to understand the feasibility and challenging of going, living, and staying on other celestial bodies. So as usual, if you have any questions, feel free to use the chat, and we will have time at the end to discuss and exchange with Sylvain. Thank you.
Thank you very much, Eva. So I will just share my screen. Okay, so thank you very much also IGLUNA, the virtual field campaign, for the, allowing me to speak about this field, which for me is very interesting. This is a part of something I'm teaching at the University of Paris for many years now. And it's a field which is evolving very quickly. So it's very interesting to see how it evolves and what nice discoveries are made nearly every day. So yeah, I'm very glad to be here to speak about this. So I'll speak about the colonization of space, and we'll see what it means and why this is so important for humanity to see what there is outside Earth and what we can do to go there and to try to live there. And so I decided to speak about different things around colonization of space. And so as Eva said, it's I just wrote a book on the Colonization de l'espace in French. So it's a book which in fact begins with the colonization of Earth by life, and then see what are the possibilities of colonizing other places in the universe. First the moon, of course, the solar system, and then we go further with the planets. And also there is some, I write a bit on the debate about colonizing other planets and the ethical questions about this and things like this. So it's a very illustrated book that I find very nice, and which is quite funny is that it went out exactly during the confinement period. So it was strange to be always at home when while some journalists were interviewing me about going out of Earth and going to space. So I will split this presentation in 4 parts. First, very briefly, I will speak about the context, why we speak about this. In fact, why today at this time we speak about colonization of space. Then I will see the possibilities of colonizing the solar system. And then we'll go further with colonizing the exoplanets. And I will finish with a question that Enrico Fermi had asked a few decades ago, which is, where are they? Which means, where are the extraterrestrials? Which in fact is related to this question, because if we want to colonize space, it also suggests that some other life in the universe have wanted to colonize space. Okay, so first part, the context. All the illustrations are taken. I mean, for these, the titles are taken from my book. So, colonization of space, part 1, the context. I just wanted to begin with the fact that this is a subject that we speak about that was spoken about for I would say hundreds of years or even more, thousands of years. And some astrophysicists, like well, astronomers, I would say at this time, like John S. Kepler, wrote a book called Somnium, where he could imagine someone going to the moon, an Icelandic boy going to the moon. And then there is this tale by Savinien and Cyrano de Bergerac in the 50s, who wrote a book about entitled The Other Worlds, Empires of the Moon. And then there was a second part where he was going to the sun. And what is, well, there are some funny parts, for instance, how to go there. You see on this picture, how he managed to go to the moon. He's within something which, in fact, does some fireworks, and he goes like this to the moon. So it looks very funny now, but in fact, what is also interesting that it looks a bit like we went to the moon with Saturn V. And there, when he arrives to the moon, he finds something which first looks like the paradise. And then, in fact, when he is on the moon, the people on the moon looks at him very strangely, well, like in fact, as a stranger, and they don't like him. And so they put him in jail, and in fact, he has a life which is very harsh. And so it's a philosophical tale about looking at stranger people, at people that you don't know. And it is very interesting in the context of if we find some life outside of Earth. And the same happens to him when he goes to the sun. And in fact, he has also some misadventures on Earth. So it's everywhere there are strangers. And the other tale I wanted to speak about was the very famous Jules Verne tale From Earth to Moon, which is 2 centuries later. And then you see this bombs that are sent to the moon. So of course we can't imagine people inside these bombs surviving to this launch. But so they go to the moon, and what is interesting this tale is that Jules Verne describes very precisely what equipment they have to bring there to go to the moon, to survive in the moon, and to explore the moon. So of course now we don't plan to go to the moon either way, but it's interesting to see that people have always imagined to go to the moon. I mean, probably because it's very close to us, it's very bright, so we want to go there. So I want first to take a step back, and before speaking about colonization of other worlds in the universe, speaking about how has life colonized Earth. And you see here the Petit Prince, who is on his planet, and obviously this is not a planet where there would be life. You see, there is no atmosphere, there is no water. So in fact, what do you need? The only thing that Petit Prince has here is a rocky planet. So what do you need to colonize a planet, or what was on Earth to allow life to colonize it? Well, first, like the planet of the Petit Prince, it was a rocky planet. It is a rocky planet. Also, there is an atmosphere, which allows many things to breathe, of course, but also to avoid big gradients of temperature, as we will see later. Of course, there is liquid water, and this is very important, not just for us or for the living beings on Earth to live, to breathe, to have some water to live. It's also because molecules assemble easily in a liquid form, more easily than if it's gaseous or solid. Then the temperature on Earth is between 0 to 40 degrees. You will see that this is important for water to be liquid, and also not to be too hot, because if it's too hot, the molecules are destroyed. Then there are other things that we are not sure if these things are very important for life to be present on the planet, or for life to colonize the planet. Earth has a magnetic field, which is quite strong, which allows to make a shield, magnetic shield, to protect against the stellar wind, and more precisely against the solar wind, which are very energized particles which arrive on Earth and, well, can cause cancers and genetic mutations. So it's useful to have this magnetic field. And this is created by a rotating core inside the Earth. And the last thing, that the Earth has a moon, which is a big satellite. And this satellite, as we can see from the Earth with just binoculars, we see that the moon has many craters. And the craters that the moon has is craters that the Earth didn't have, because many asteroids who passed close to the moon crashed on the moon. But without the moon, they could have crashed on Earth. So it's useful to have this big satellite. We don't know if without any big satellite, the Earth would not be colonized. But with a big satellite, it's easier because you shield from meteorites. And also the other advantage that you have some tides, periodic tides, and this could help also for us to, for life, sorry, to colonize Earth, to develop and colonize Earth. So how has life colonized Earth? Where we see there are many ingredients, and one of the ingredients which is in fact visible from outer Earth, from space, and from very far from Earth, is this blue color, which in fact is, of course, due to water. And I always ask to my students, is there water on Earth? Is there water on Earth? Well, of course, there is water on Earth, but is there a lot of water on Earth? Well, of course, there is water everywhere. We see it's blue. The Earth is blue, so there is water everywhere. But do you think there is really a lot of water on Earth? And when you take all this liquid water, which is in the oceans, when you take the water which is in the atmosphere, you take everything and you compare it to the size of Earth, and in fact, there is not a lot of water. Of course, there is also water inside Earth. But the water which is accessible to the living beings on Earth, and which allows life to appear on Earth, there is not much water. So, which means that we have to protect this water. In fact, the Earth is a very fragile system, as we know. But this image, I think, is one of my favorite, because it shows really that there is not a lot of water on Earth, and you have to take care of water on Earth, and of Earth also. So then the question is, well, because we want to speak about colonization of space, I'm here for this. But the question here is, why should we live? Why should we live? Well, we might want to live because we want to explore other worlds. We have always done this. Neanderthals, Homo sapiens have always migrated, discovered other things, perhaps because they wanted some more food, perhaps they wanted more water, perhaps they wanted just to see what there was beyond this point. So we want to explore, and we will see that we have already explored a big part of the solar system. And we are exploring also the rest of the universe, of course, not going there physically, but we send probes, and we also observe them with telescopes and satellites to discover many things. So we might want to live just because of this, just to discover some other things, like Colomb discovered America, and Magellan made the tour of the world. We could just want to try to discover some more things. There are other reasons that are not probably so, that are more pragmatic, I would say. For instance, the loss of biodiversity. Well, you see this these emperor penguins there, which have, it's not the most endangered species, but there are many species that disappear today, and we speak about the sixth extinction, like loss of biodiversity. And this might be a problem for human beings also. So this might be a reason for Earth, for people to try to go to another place. There are, of course, reasons that are related to climate change, pollution, and things like this, which of course all are related also to loss of biodiversity. The other reason that we know too much now is the possible pandemic, like this one we are living now. But let's think about the what we call the Spanish influenza, which killed at least 50 million people on Earth. While we might think that this could be a cause of at least a few people not infected leaving Earth to protect or to preserve some parts of the life on Earth. Well, these are causes coming from Earth, but there are causes that might come from outside of Earth, which might put us on a trip outside of Earth. Is exogenous cause, like for instance an asteroid, a big asteroid coming to Earth. So remember the 10-kilometer size asteroid which collided Earth 65 million years ago, and which destroyed nearly 75% of all life on Earth, animal life and vegetal life. So this is always possible. Statistically, there is one chance every 65 million years to such an asteroid to collide with Earth. So it might. Of course, we have the ways now to see these asteroids coming, but we don't have yet the ways to avoid them. So we can try to deviate their trajectory, but of course we have to know well in advance that they are coming, and even the calculations to know exactly where they are coming and where they are passing, if they are going towards Earth and passing near Earth. These calculations are complicated. Okay, so imagine we have to leave. If we have to leave, where are we going? Well, we have to look for Earth 2.0. Don't really like this name of Earth 2.0, but put it like this: we want to find another Earth which is nearly as good as the Earth. So this diagram shows you different stars with different brightness, and you have the solar system there, from Mercury to Neptune, let's say. And you see there is this colored band in the middle that shows what we call the habitable zone. This habitable zone, you see, there is nearly only the Earth inside. And the habitable zone means that you have a planet, rocky planet with an atmosphere, and there the temperature can be between 0 and 40 degrees. So only the Earth is inside. Venus and Mars are at the limit of the habitable zone. So looking at this diagram already, you can say, well, there is no Earth 2.0. There is Earth 1.0. There is in the solar system no other place like Earth. Okay. Presentation is finished. Well, not really, because we can look at other places in the solar system where we could try to find some other places which would be good for us or for life to adapt, to develop. So habitability zone, I said it's a rocky planet with an atmosphere, temperature between 0 and 40 degrees. You have some liquid water, but you have a very fragile balance between greenhouse effects, like what happened on Venus, we'll see it, and also divergent glaciation, which is something similar that happened to Mars. And the Earth has also a very fragile balance, And on Earth already, there have been some periods where we call this snowball period, where ice was surrounding all of Earth. So this can happen on Earth also. We can have a climate change and with greenhouse effect, which is diverging, and we can have also an ice ball around all Earth, which is also diverging. So when we will speak about other planets in other stellar systems, we'll see that this habitability zone changes and is closer to the star when the star is cool, and it's further away to the star when it's hot. That's because to have this temperature of between 0 and 40 degrees, you have to be closer when the star is cool, and you have to be further away when the star is hot. So it depends of the temperature of the star, so on the nature of the star. Okay, this is nearly what I wanted to say about the context before going to the, I would say, colonization of space. And before I go to the next chapter, I wanted to do a small quiz, and I will make like this 4 quiz at the one each at each end of each part. And the quiz number one is what is this? So I will let you think about this for 10 seconds. I don't know if you could recognize exactly what it is. It has a round shape. It looks like there are some black parts which look like craters on it. Yeah, it could look like the moon. It is the moon, but it's not the part that you are used to see in the sky. In fact, it's the dark side of the moon. It's the first image of the dark side of the moon, which was taken by a Soviet Luna 3 probe, 7th of October 1959, so 10 years before the Americans went to the moon. So congratulations for the people who guessed it. So let me go now to the second part, which is the colonization of colonizing the solar system. At least asking the question if whether the solar system can be colonized and where. First, well, let me remind you if this is needed, the solar system. So you have this sun, which is very big. Then you have 4 small planets, which are called telluric planets because they are rocky planets, Mercury, Venus, Earth, and Mars. Then you have this small asteroid belt, and then you have the 4 giant planets, which are gaseous planets, Jupiter, Saturn, Uranus, Neptune. And then you have the Kuiper asteroid belt, and then much further away you have what we call the Oort clouds, where you have the comets, or at least the core of the comets, and like the comet we see now, the Neowise, which is very nice in the sky. And well, I first said that you remember I said for a planet to be colonized better if it's a rocky planet, and so it's not the case of Jupiter, Saturn, or Neptune. So I will not speak about this gaseous planet. I will just focus here about the telluric planets, which of course already focuses a bit subject by nature. And I will speak also about one satellite of Saturn. Okay, first, the most obvious is, can we colonize the moon? This is the moon shown in false colors, as you don't see it because normally you see it very white. This is when you, when in fact it's seen as less bright, you can see these colors that appears on the moon, but you don't see that with the eye. Well, there are many plans to go to the moon. I will not describe all the plans, but I could just say, for instance, that NASA just awarded a $200 million contract to Astrobotic Technology. The plan to send a lander to carry the first rover to be sent to the moon surface first rover after the one from 1972. So in 2023, which means that nearly for 50 years, there will not be any return on the moon. And the plan, of course, is to, well, in this case, to search for ice that could supply water for astronauts. And the plan later is to send some astronauts on the moon. Let's go with this. Now, there are some rovers on the moon, like, for instance, the Chang'e 4, Chinese one, which is on the dark side. And so this was a challenging landing to land on the dark side, because when the probe is on the dark side, you cannot communicate with Earth. So you have to send another probe, which is orbiting moon, and you communicate with this second probe, and the second probe communicate with the lander, and they successfully landed on the moon. But they didn't send anybody yet. So the plan, when you speak about colonizing, of course, we don't speak only about robots, but we speak also about people. So there is this Artemis plan, which is an American plan with European collaboration to send people and robots on the moon in 2024. I think this date will slip a bit. So there is this SLS launcher, and then the idea is to build a gateway station which would be close orbiting the moon, and you would have an Orion module which has an European collaboration, and this Orion module would go from the Earth to this gateway station. And in this case, you can begin to send material, robots, and also people on the moon. Of course, it will never become Earth 2.0. There is no atmosphere on moon, but the aim in a middle or long term would be to build a moon village, which is something that was a term that was invented, I could say, by the ESA director in 2015, I think. And the aim was to install a permanent human robotic presence on the moon. And the moon has many resources, because if you go to the crater which is close to the southern pole, then you have some water, solid water, some ice inside the craters. And so you can use this water, of course, to make some air to breathe, but you can also use it as water. You can use the regolith, which is the dust of the moon, which is created by all the asteroids falling to the moon. You could use this regolith to build some domes on the moon. This is what you see on this artistic view. And you can also use the helium-3, which is on the moon, as a fuel. Of course, so you can live there. You see all the people there on this artistic view have they are like astronauts on the moon. You cannot walk like this without having something to breathe. So they have all what is needed to breathe when they walk on the moon. The idea probably is not to bring many people, but the idea would be probably to be like a spaceport to go to the solar system. And you can go to the moon, and you can launch some rockets from the moon, which has less gravity, so it's easier to launch from the moon than from Earth. And then you can go to the solar system and explore the solar system. So the moon is an interesting place. As I said, it's not the Earth 2.0, but it's a good starting point to begin to colonize the very close universe, very close to Earth. Speaking about the moon, there is a planet which is very similar to the moon. I just, before I go to the planet, just want to mention that on the moon, its temperature is between nearly 150 degrees during the day and nearly minus 100 degrees during the night. So be prepared to big temperature gradients. But there is even worse in the solar system. For instance, with Mercury, which is the planet I'm showing now. Mercury is very craterized like the moon because there is no atmosphere, so there is no erosion. So when you make a crater there, the crater will stay forever, which is not the case on Earth. I show you Mercury in full colors so that you see that there are differences in the terrains on Mercury. And on Mercury, the temperature gradient is even worse than on the moon because it's between minus 150 and plus 450 degrees. So there you have very strong temperature gradients. Probably it's hard to survive on Mercury, even with protective dressing. You have, like in the moon, you have in the craters which are close to the North Pole or to the South Pole, you have some ice, water ice. So you could do the same than on the moon. You could exploit the ice, the water, which is in the soil of Mercury. Problem is the high temperature. There is a very tiny atmosphere on Mercury. Probably because of this high temperature, it's not the best place to even to have a spaceport on Mercury. Okay, so forget Mercury. Let's go to the next one, which is Venus. Venus, the goddess of love, has clouds which are very thick, so thick that in the 1960s, people thought that there was a luxuriant, gorgeous vegetation, like a bit like in the tropics on Earth. When you send a probe which can use radar to look through the clouds, you can see that Venus is not exactly like this, like paradise. And this is another probe. So this is the Magellan probe who made these images. And what you can see is that the landscape looks a bit desolate with some volcanoes there and even some basaltic lava. So it's very desolate. Temperature is of plus 470 degrees. It's hot. It's not the worst. The worst is that you have a pressure of 90 times the pressure you have on Earth. And also you have some rains of sulfuric acid. So I don't know if it's the goddess of love, but it's a passion which is very dangerous. So probably the Venus will be hard to colonize, except if we try to terraforming Venus. We'll speak about this later, but it will not be easy. Okay, so the next Earth, you know already. So the next planet in the solar system is Mars. Colonizing Mars. Mars is in some way very similar to Earth, nearly the same size, a bit smaller than Earth. Gravity is 38% of Earth. Same duration of the day on Mars, the same seasons. So you would not be too, you wouldn't feel too strange on Mars. In 1666, Cassini discovers polar ice caps on Mars, so which means that there is some water ice, and this has been imaged then later, much later, with the Mars Express probe, for instance. You have here the ice caps on Mars. Then you have this very nice story that I have to say very quickly, but in 1877, Giovanni Schiaparelli saw some what he called canali, which in Italian means a structure which looks linear, but it's not. It can be natural structure. So he made a map of this Mars. But then there is this very rich and passionate American businessman, Percival Lowell, who saw also these what he called channels, but in his head it was more like artificial channels, and he thought these were channels to take some water from the polar ice caps and to bring it to all the cities that there are on Mars. So you have this very nice map of Mars with the irrigation channels, and well, he was even invited by the Nature editor in 1907 to speak about what was the status of the Martian life at this time. So at this time, we really think, at least some people really thought that there could be some life on Earth, and probably this allowed to begin the myth of the Martian that, in fact, still stands today. We still want to find some life on Mars. Temperature on Mars is between minus 100 degrees to plus 0 degrees. So on the 21st of June, on Mars at midday, you have 0 degrees, which is in fact not bad. It's probably something similar to Antarctic. But it's better than what you have on Mercury or on Venus, for instance. Which explains why, all of this explains why there have been many missions on Mars. The first one, American mission, Viking 2, 1976, landed on Mars, looked for Martians, didn't see any people walking on Mars, but they did see some frost, which means that there is water on the surface of Mars. They saw also that the rocks were covered with dust. They saw they could analyze the composition of Mars, which is very similar to the composition of the crust on Earth. So either from volcanic or from sedimentary origin. They could show that there was some presence of water on the Martian soil, and now with all the probes we sent to Mars, we confirm that there is water everywhere on the Martian soil. But the Viking already made an experiment that they showed that there was no organic molecules, no life. So organic molecules is molecules with carbon and hydrogen in the molecule. So at least for a few centimeters below the surface, there was no life. Perhaps there is life below this, but not on the surface, and not for a few centimeters below the surface. And already at this time, they were very careful not to bring bacteria from Earth to Mars. And this is a picture taken in 1975 with the Mars Viking lander, which is sterilized in an oven at a high temperature, something we don't do now at such high temperature. And there is always try to sterilize the probes, not to bring bacteria from Earth to Mars, because obviously, if you bring bacteria on Mars, and if there is some life on Mars, then you destroy all the life that there is on Mars. And it would be a pity, because it would be nice to see if life has appeared in some other place than Earth, and to see how it developed, if it appeared. So, just show a few images of some probes, like Mars Express, for instance. You show this picture around, you see a bed of a river, and you see in the blue parts, this suggests the presence of ice. It shows the presence of ice, sulfates, and also some clays. And who says clays says water, which means that there was a lot of water, liquid water on Mars that was present in the first probably billion of years of the planet Mars. You see also some crater impacts, which are very interesting, because this is something you can see when you throw a stone on a wet sand, and you see that it will make a splash. And in fact, what you see around the crater is that the water that was in the soil of Mars just boiled up, and then came to the surface. So you see this splash around the crater, and this shows that there is some ice water in the soil of Mars. Something even more impressive is that we can now see some places which are the fossil of old tsunamis on Mars. This is the trace of a giant tsunami which was created by an impact on Mars between probably there is 3 to 3.5 gigayear, with a wave of 300 meters high, breaking at 220 kilometers over a distance of 1,200 kilometers. And here you see a model of this tsunami which is evolving. So this is very impressive. Now there is a probe, an American probe, which is called Curiosity. This is a selfie taken by Curiosity. It's a mosaic selfie taken by Curiosity. And this is the path followed by Curiosity. And well, now I will show you a video of Curiosity going to Mars. So now the question that Curiosity, for instance, want to answer is there life on Mars? And there is a polemic with the methane, because the methane was detected on Mars. And in fact, if it's detected, it means that there is some source of methane, which can be either volcanoes, so geological source, or bacteria, so biological source. And there is a European probe, which is a trace gas orbiter, which is now trying to answer this. So this would be interesting to see if there are bacteria now on Mars. But what happened on Mars? Why was there so much water? Now there is no water left. Well, what do we think? That the atmosphere on Mars just disappeared. Like since 3.6 gigayears, the atmosphere disappeared, and then the water on Mars disappeared. And this shows that the environment can be very fragile, as it can be on Earth. And so this is the summary of what you have on Mars. With you have also some regolith on Mars, like on the Moon. You have some strong wind on Mars, and you can have some perhaps you have some water in the soil, and perhaps some life, we don't know, in the subsoil of Mars. So there are many missions that are planning to study this planet. For instance, there is this ExoMars, European and Russian mission in 2022, which will look at which will drill the soil of Mars for 2 meters. And then there is this Mars 2020 American mission, which will also take some samples of Mars. Mars is very studied, and we saw that it's very close to Earth, and this is why people have imagined terraforming Mars. So what is terraforming? It means that you can try to change the atmosphere, and at least locally, like you would see here, to build some small cities where you could breathe like this without just you go out and you breathe like this. Of course, there are some questions, because how do you protect from the asteroids, for instance, which could break this protection, the shield protection around these cities? This we don't know. For Mars, we would have to put some, probably some methane, for instance, to increase the temperature of the atmosphere. Okay, so for the theoretic planet, it's all. We don't have more planetary planets, but we have something interesting in the solar system, which is Titan. Titan is the satellite of Saturn. This is the view from Earth, so you don't see much. This is the view from Voyager. You see some atmosphere. And this is the view from Cassini, which is a probe, American and European collaboration probe, which went to Saturn, took some pictures of the Titan. Titan is the satellite of Saturn, which is quite big, 5,000 kilometers diameter, and the only one with an atmosphere. And there are some oceans of liquid methane. So if you like swimming in liquid methane at minus 180 degrees, Titan is for you. You have some clouds of methane also. And well, there is a probe, Huygens, which plunged into the atmosphere of Titan and which survived in the environment of Titan with very cold temperature. And here you see a few pictures that the probe took when it was approaching the soil of Titan. With you see here an island in a great lake on the surface of Titan. And here you see it is approaching something which looks like a landscape around the sea on Earth. And there you see a few hills there. And there you arrive on Titan. This is a picture of the landing site. So as I said, the temperature is very low, but you see there are some stones that have a round shape, and this shows that there are some tides. So there is some liquid on Titan, but it's liquid methane, it's not liquid water. You are at minus 180 degrees. And under the soil of Titan, you have some ocean of liquid water this time. So you could imagine that there could be some life below the surface of Titan. So it's a very interesting satellite, which will be explored by a Dragonfly mission probably in 2034, so in a long time. So a drone which will go to Titan. Okay, in the solar system, there are also comets like Halley, Churyumov-Gerasimenko, Oumuamua, the Neowise that we are seeing now. We will not colonize this, but we could exploit the resources of these celestial bodies, like to do some interplanetary trips, for instance. And this allows me to arrive to the second question. What is this? And so I leave you for 10 seconds to think about this. This is a small bright dot in the middle of something which looks like dust. And in fact, this is the pale blue dot taken by Voyager 1 in 1990s, where you see, in fact, the Earth. And around the Earth, you see this dust, which is coming, in fact, which is the origin of the planet. Planets have been made of dust, which is visible here. Okay, so this brings me to the part 3, colonizing the exoplanets. Exoplanets, well, they are hard to detect because the star is always much brighter than the planets, nearly 1 billion times brighter. Well, I cannot avoid mentioning here the discovery in September 1995 by Mayer and Kellos, who won the Swiss astrophysicist who won the Nobel Prize last year for the discovery of the exoplanets, the first extrasolar planet, 51 Peg B, which was like a Jupiter planet very close to the star. Now we know 4,282 exoplanets, so it's a lot of exoplanets, but obviously not all of them look like Earth. And on this diagram, you see that we found some what we call the hot Jupiters. We are planets like Jupiter, massive but very close to the star. We discover also some Jupiter's planets, some hot Neptunes, and also some super hot Earth, which are so nearly to 10 times the mass of the Earth and nearly closer to the star. And what we want there is to find an habitable exoplanet. So this is the diagram I showed earlier, where there is also another planet, Gliese 581, and you see that when the star is colder, you have to be closer to the star. And we know now some planets which could be potentially habitable, and there is one here on the left, which is called Proxima Centauri b, that I will now describe briefly. Wait. So it's a closest star at 4 light years, so it means 40,000 billion kilometers. It's a triple system, but you see here Proxima b, the planets, which has an orbital period of 11 days, so very close to the star. And the question is it habitable? It's the closest of Earth, but is it habitable? Well, we don't know. And in fact, you see on this diagram, you have the radius versus the mass, that depending on the observations, depending on the models that we put there on the observations, the planet is either rocky or it's an ocean planet. We don't know exactly what is the real nature of the planet. So what do? Do we go there? It would take 70,000 years to go there. So I don't want to go there. But there is a project now, which is called Breakthrough Starshot, which is sending probes to Proxima Centauri at a velocity of 20% the speed of light, which means 20 years of travel. At this velocity, you reach Neptune in a few days. And you send thousands of probes of weighing nearly 1 gram with camera navigation communication, equipped with a nearly 1 gram solar sail powered by a 100 gigawatt laser, and you arrive on Proxima in 20 years. Then you send back the picture, which comes back in 4 years. In 24 years, you know if it's a rocky planet like Mercury or an ocean planet. And you see if it's worth going there and spending 70,000 years to go there. There are other planets like this. For instance, this TRAPPIST system, which it's a very cold star, but it looks like the planets could be habitable. And you have even some artistic view of people going to this system and discovering this one of these planets. So it's the planet Hop, and you have the Hub Zone vacation, voted best Hub Zone vacation. So we can dream, of course. So we don't go to these exoplanets now. We cannot send probes there, it's too far away, but we can observe them. And the two future best ways to observe them is the James Webb Space Telescope from the NASA, which would be launched next year, normally, and the European Extremely Large Telescope, which first light could arrive in a few years. And the aims are to analyze the composition of the atmosphere of these habitable planets and to see if really they are habitable. And this brings me to the third quiz. What is this? And then I will show you a video, and at the end you tell me what it is. So this was, in fact, not Mars, but it was a view of the Atacama Desert taken by a friend, Serge Brunier, with conditions very similar to what you have in Mars. Very briefly, I will now answer to the question, where are they? Well, I will not answer to this question, but I will ask the question. Where are they? You know that we are, if we want to colonize space, then we are not the only one to colonize it. If there is another civilization, and of course, we have already given signs of our presence. For instance, we sent a probe like Pioneer 10, where we have sent a map of where we are. So if extraterrestrials want to find us, they can find us. And then there is this direct equation, which when you take all the consideration about number of stars that have planets, number of habitable planets, number of planets where life emerges, etc., etc., you arrive at nearly one planet on which there is life capable of broadcasting, capable of sending signals. So if this is the case, if we are the only one, then it's strange. And it's very strange, but the answer could be that there could be many civilizations, but each intelligent civilization lives only for a short time. And at some simultaneous time, we are the only one. And so this is the Fermi paradox. Where are they? We don't know, but perhaps there are not any other. We have not found any other civilization yet, but it's like diving into an ocean and after finding empty, you said there is no fish in the ocean. So I will finish with the last quiz, which is what is this? Probably you know it now. This is a geoglyph looking what it is called the astronaut in Nazca, Peru. And I will finish with I will not finish with this. I will finish with this slide, which is my favorite, which is the Apollo 8 first extraterrestrial vision of Earth. And the astronauts said, we went to discover the moon, and we have discovered Earth. Thank you very much.
Thank you, Sylvain. That was really interesting and very dense. So we have many questions going in many directions. So I will select some of them. First, you talked about terraforming other planets. We were wondering about the ethics behind it.
Me too. Yeah, I think if there is some life on a planet, my point of view would be not to go there. If there is no life on a planet, my point of view would be, are we really sure there is no life on the planet? And if we are sure, then I would try to make less harm as possible on the planet. I'm not really in favor of terraforming.
Yeah, speaking of life, what is considered as sign of life? What are the conditions to be considered as life?
Well, life, you have different definitions, but one of the definitions is that it's an open system which exchanges energy with the exterior, and also it's a system that evolves like in the Darwinian sense, in the sense of evolution. So for instance, a virus, there is a polemic on this, but a priori, a virus is not a living system because it needs something to be in to live.
Another question regarding life, can life be possible even if they are affected by a strong radiation dose? With a lower atmosphere density on Mars and the Moon, do you think life is possible on other celestial bodies?
Yeah, this is a very good question, and indeed, this is a very big problem. The solar wind is very dangerous, so we don't know what is the effect of the solar wind for a long time, and this is not too much a problem for the Moon, but it is for Mars. because for Mars, for the Moon, you go there in 4 days, and you come back in 4 days. So in a week, nearly you have disappeared. But people disappear for a week, and that's okay. They're on vacation. But for Mars, you leave for 6 months to go there. You stay there for 2 years because you need the Earth to go around the Sun like Mars, and then to go back, you need another 6 months. So nearly 3 years, and you are bombarded of solar wind for 3 years. And this we don't know what is the effect, but probably not very good. So this might be a real limitation of, for the moment, of interplanetary trips.
And what do you think about living on asteroids?
Living on asteroid is not very easy because any small movement that you make, you are ejected from the asteroid. So because the gravity is very small, so you just do this and then you're ejected into space. No. Well, what you can do is, if you want to exploit the resources that you have in the asteroid, this you can do, but I wouldn't say to live on an asteroid. You have to live like this, you know, on the asteroid to grab it always. It's not very fun.
And to avoid the impacts of asteroids on other bigger planets, what do you think of the joint NASA-ESA Hera mission? Do we have technology to deviate asteroids from their trajectory?
Well, at the moment, it's what they are trying to do is to see if they have, if they can do this. Probably on small asteroids, which can do a lot of harm, it might be probably possible. For big asteroids, I think it's probably not possible in the short term. So our best chance is statistics. There are not many big asteroids, so let's hope that there is no big asteroid that will hit us before a long time. And also there is a lot of ocean on Earth, so if it's not too big, it can fall into an ocean. It's not too a problem.
Another question is, what are your thoughts on colonizing and exploring other systems? And on that point, what do you think of the Breakthrough Starshot initiative to Alpha Centauri?
Well, I spoke a bit about the Breakthrough Starshot. It's not a way to colonize the system. It's just the Breakthrough Initiative just to take pictures of Proxima Centauri B, and that's it. The probe will go there. They go very fast. So they go there in 20 years, they take a picture, they send back the picture, and then they go on. So there is nobody in the probe. It's just a 1 gram probe which goes there, take a picture, and you have the picture in 24 years, which means that if you send it now, in 2044, you have the picture of Proxima Centauri B. And the probe went at 20% of the velocity of the light. This already shows that it's very far away. And in fact, it also answers the question, is it possible to colonize exoplanet? Now, I think it's not. It's too far away for us. It's already, you see, quite long at this velocity to send some probes, very small probe. So to send human beings there or life there, I think it's still very far away. Let's first concentrate on the solar system, which will be already difficult, as you said, for the solar wind, for instance. And let's also take care of the Earth 1.0.
Maybe one last question. When do you personally think we will get to colonize other celestial bodies? Please being as realistic and sincere as possible.
The question is when?
Yes, when do you think it will happen?
Colonizing, it depends what we think about colonizing. If it's only sending robots on the planet, we already colonized Mars, because we can send robots on Mars, we can send robots on the Moon, so this is done. If it's sending people, we sent people on the Moon already. I think nobody could say that we colonized the Moon. But if you can send 10 people on the Moon. I think it's feasible with all the technological way we have now. We can send 10 people on the Moon. Okay, that will live there. Is this colonized? I don't think this is colonizing the Moon. Colonizing for me means really we live there and we don't think about coming back to Earth. And Sincerely, I would say this is not happening before a long time. And I hope that we will do it because we want to do it, not because we have to do it because the Earth is not in a state where we can live on it.
Yes, one last question. What could be the reason for the disappearance of the atmosphere on Mars?
Well, yeah, sorry, I probably I was a bit quick on this. So we have some observables that the probe, the MAVEN probe, showed that the atmosphere was disappearing on Mars at a rate which was quite high, and probably this has begun probably 3 billion years ago, and probably this is because Mars doesn't have any or has a very weak magnetic field. So there is no shield against the solar wind. And so the solar wind interacts a lot with the high atmosphere of Mars, which is not the case on Earth. Earth has a very strong magnetic field. So you have this shield, magnetic shield, and the solar wind cannot go directly to Earth. It just avoids Earth. And then some of the particles go to the polar caps, and this creates the aurora that you can see in the sky. But so majority of the atmosphere on Earth is protected because of this magnetic field, which is not the case in Mars.
Okay, great, thank you. So we have to finish now. We are already a bit late. So thank you for this very interesting presentation. And we hope that our viewers are now able to understand a bit more the challenging of living on other planets. And so join us tomorrow. Tomorrow is the last day of the public presentation. So we'll have Team Power Hub and Team Rover presenting. And in the afternoon as well, our Swiss astronaut Claude Nicolier, who will, following Sylvain's thematic about the future missions regarding the exploration of the moon. And to conclude, tomorrow is Alexander Gerst, ESA astronaut, coming to explain us his Horizons mission, and we will have a Q&A session with him. So thank you, Sylvain, for joining us today, and thank you all for watching. Bye-bye.